Okay. Now, so this is the basic idea, right. So, let us actually take a look at a very popular Opamp. Is perhaps the highest selling chip in the history of electronics, right. It is the 741. Let us see if I can download the picture rather than draw it. Make you so this seems like an okay op amp, right. And early op amps were indeed kind of designed based on this fundamental principle. Unfortunately, it turned out that a lot of op amps people were getting fed up of them in the field, right. So, they work nicely in the lab, but once in a while the output of the op amp would latch up, right. And so, what the problem was the following. The problem was that remember you all know device physics, so you will be able to understand this. So, in a MOS transistor, let us say the transistor goes into, the gate goes very high and the drain goes low, right. Let us say you are building a common source amplifier, the gate goes very high, the drain goes low. When the drain goes too low, the transistor goes into the linear region, right. In an NPN transistor, when the base goes very high and the collector goes low, when the transistor goes into the saturation region, right, what actually happens inside the device? Yeah. So, I mean in the active region, the base emitter junction must be forward biased and the collector base junction must be reverse biased. When the transistor is operating in saturation, right, the collector base junction gets forward biased. So, basically that means that whatever happens at the base will also reflect at the forward bias. What does it mean? That basically means that the collector base junction is a short circuit. So, if you yank the base, if the transistor is in the active region, if you yank the base up, the collector is going down. Whereas, when the transistor is in saturation, you yank the base up, the collector is also going up. Now, this is a serious problem. Why do you think this could be a serious problem? Remember, when you put negative feedback around an op amp, right, you are assuming that all the transistors are operating in the active regions, right. So, now let us say by some some mistake or some transient, many times what happens is that it takes time for the supply to come up, right, but the input is already there, okay. Under such circumstances, it is very easy to come up with scenarios where the common mode of the input, the common mode voltage of the op amp inputs, right, that exceeds the supply. Under such circumstances, then it is only normal, the input pair transistors will be in the saturation region. See, if the supply voltage is lower than the common mode voltage of the input, right. So, the input common mode is greater than supply. What happens? These transistors will become saturated. So, basically whatever happens here, same thing will happen here. So, what is supposed to be negative feedback, you had gone and arranged the signs of the op amp so that there is overall negative feedback. Now, what happens? The input transistors are saturated and the negative feedback has become positive feedback, and there is enough gain in these transistors to basically cause the loop gain to be greater than 1, but now with positive feedback. So, what will happen? I mean, if you flip the signs of the op amp in a negative feedback loop, what will happen? The output will go to either plus VDD or to ground, it will saturate, right. And so, it will get stuck in that state and stay there, and the only way to fix the circuit would be to turn off the supply and turn it back again, right. And that of course is not a good thing, because you have to, just imagine you are on a satellite in Mars and like to go into Mars and suddenly something like this happens. There is nobody to go and switch off the circuit in outer space and then switch it back again, correct. Okay. So, or imagine your phone and like you are talking in the middle of a very interesting conversation, and suddenly the whole thing just goes off, and then right at that time I'm sure you're not thinking oh, well the guy should get marks for steps because well it's working almost all the time, only once in a while it does this weird thing. Okay, and I turn it off and turn it on. Right, all of us know how annoying that is. Right from a computer hanging in the middle of something to a phone. Okay, so you basically want this stuff to work, right, no matter what. So this was clearly a big problem, right, and so the root cause of the problem is that what is the root cause of the problem? The root cause of the problem is that in our common source amplifier or whatever we build, let us assume that this is some resistive load, right. The root cause of the problem is that when the transistor is in the active region, the gain from here to here has one sign. When the transistor is in saturation, because of the effective short between the collector and the base, the sign of the gain is the opposite sign, correct. So that basically so the root cause is basically the fact that we are taking, what is the transistor doing? Basically it's converting this voltage to a current and pushing that current through a resistor, right. So the root cause of the problem is the fact that we are taking the output at the collector, correct. Okay, I mean if we didn't look at the collector terminal at all, if we found some other way of taking that current in the transistor and passing it through a resistor, then the problem would be, I mean the root cause of the problem is we are looking at the collector terminal as the output. So that when the transistor saturates, we are in trouble. So the thinking was therefore that this led to the thought that, well, the collector current and the emitter current are the same, correct. So if I if I tapped off the emitter current rather than the collector current and pass that current through a resistor, then I would be able to get, there is no issue of I am not messing with the collector at all. So I will actually ground I mean increment, I mean I will connect the collector to VDD, right, and I will only look at the current through the emitter. But there is a problem, right. What is the so if you want a current, what I mean if you want a current source, what should be the output resistance of the current source? Must be, if you want a current source, what I mean in other words, when you are looking at the collector, what is the output resistance looking in here? When the source is grounded, what is the when the emitter is grounded, what is the incremental impedance looking into the collector when the transistor is active? It behaves like a voltage controlled current source, so the output impedance is infinite, correct. Okay, now if you say, okay, I am going to look for current in the emitter, what comment can you make about the incremental output impedance here? 1 by Gm, it's actually a very low impedance, right. So it you want a current source so that you can push that current through a resistor to get a lot of voltage gain. But now unfortunately our so called current has got a very low output resistance. So so if you want to take a current with a low output impedance and make it look like a current with a high output impedance, what kind of control source will we use? Current control current source. So what kind of current source will you use? What is the simplest current control, single transistor current source you know? Common base. So do you want to use an NPN common base or a PNP common base? Current is flowing like this. You use a PNP common base amplifier, right. So VB Okay, yes. Okay, if you put NPN, what will happen? Well, see, the advantage of using PNP is that the same quiescent current can flow through the PNP transistor also. Okay, you can also fold. I mean that I think that's also possible, but this is what does make sense. Okay, so now this represents a current source, right? So if I apply a incremental Vi here, so let us say this is VCM plus Vi, this is some bias voltage Vb, this is VCM minus Vi. What comment can we make about the quiescent current here first? Let us assume all the transistors have the same saturation current Is. Is exponential. Yeah. So, basically simply by symmetry this is VCM, this is VB, correct. So, by symmetry the voltage in the middle will be half. So, this is basically VCM minus VB by 2 VT, correct. So, there is some quiescent current, and what comment, if you assume that the GM of these transistors is denoted by G sub m, right. What comment can you make about this incremental current? Let us assume beta is infinite. What is this voltage for incremental signals? It is ground. So, basically what you have is something like this. Okay. So, this is Vi, this is ground. I am interested in finding this current I. GM Vi by 2, correct. So, this is nothing but this voltage is Vi by 2 by symmetry, correct. So, this will be GM Vi by 2. So, that is the current that is flowing here, small signal current there is GM Vi by 2. Okay. So, okay. Now, to get lot of gain, what kind of load do we want to use? Do we want to use a resistive load or do we want to use something else? Active load. So, basically one way of doing this would be to just put an active load like this. Okay. But now there is a problem, the problem is the following. So, the current, as you can see, the quiescent current here is Is exponential VCM minus VB by 2 VT. Okay. So, if the input common mode changes, what comment can you make about about the quiescent current flowing through the transistors? If VB is fixed and the input common mode changes, the quiescent current will change exponentially, right. I mean at a pinch, if it goes up you may be happy, but if VCM goes low a little bit, then the current will you basically you will have almost 0 current in the transistors, correct. And compare that with our conventional differential pair. When we change the common mode voltage, what comment can you make about the current in the transistors here? It does not change, correct. So, here therefore, so if we simply did this, right, why did we do this? This avoids the problem of changing. What was this? Why did we go to this in the first place? Yeah. So, basically the output would latch, right, because of change of the sign of the feedback. So, we said we are going to take the current from the emitter rather than collector. Now, we have a new problem, right. The problem is that the bias of the common base point, right. If it is fixed, then if the common mode varies, well, the current will also vary, which is no good, right. We want the quiescent current in the transistors to be constant, right. So, okay, so how do we fix the problem? If VCM changes and we want the quiescent current to remain the same, what do you think we should do? We should also, VB should also change so that the current flowing in the transistors is the same, correct. The quiescent current flowing in the transistors is the same, alright. So, in principle what will we do? I mean, we can't measure the change in VCM because it is coming from outside, we have no this thing, right. What do we want finally? We want the sum total of the currents in the two transistors of the input pair to be, that is what this guy is doing, correct. What is happening here? The sum total of the two currents in the quiescent currents in the input pair is always maintained to be a constant. So, we would like to do the same thing, the same thing has to be done here. So, we want to find the sum of the currents, quiescent currents in transistors Q1 and Q2 and tweak the base voltage so that the sum of the currents always remains constant, right, equal to some reference current. So, where can we find the sum? Is there some way of finding the where can you put an ammeter to find the sum of the two currents in the transistor of, I mean, the sum of IQ1 plus IQ2? What do you think we can do? Where can we measure? Okay. So, well, good place to measure is the collector. So, in principle what you would like to do is put an ammeter here, right, measure the current IC. If IC is greater than Iref, right, which is the constant current you want to flow in the input pair. If IC is greater than Iref, what does it mean? It means that VCM is too high, right. So, or in other words, you have no control over VCM, it is only VB, VB is too low, and what should you do? You increase VB and vice versa. So, if IC is greater than Iref, must increase VB, correct. Okay. So, basically we need to therefore find, I mean, you need to compare IC with Iref. What is comparison? Yeah, use KCL to compare, but so basically you make, so one way of doing this is to make a copy of this current. How do you make a copy? Current mirror, right. So, this is the current mirror, okay, and then you will compare this with, this is Iref. So, this is IC, this is also IC, okay. So, this is Iref. If IC is greater than Iref, we must increase VB, but what happens to this node X? If IC is greater than Iref, the node X increases. So, what should we do? Well, the easy thing to do is simply connect IC to, right. So, this is basically a feedback loop, always comparing the total current in the input pair to Iref and changing VB in the right direction and the right amount, so that the current, quiescent current, is always equal to Iref, okay. So, this basically solves the problem of the transistor going into saturation, then causing a negative feedback loop to become positive feedback. Does it make sense? Okay. And so this is the I mean, I don't know if you are able to see this, but this is, I thought this is an incredibly clever idea, right. and something which is not obvious at all.